Hi, everyone. Welcome to our free webinar focused on causal inference and real world evidence. Today, we are joined by somebody who has been working in this industry for more than 10 years. He holds a bachelor degree in mathematics and statistics. And alongside that, he also holds a master in economics from the Université de Montréal. He's currently working as a statistician with JB Statistical Consulting and is currently working as a lecturer of data science at HEC Montreal. An experience so good that it's our fortune to learn from him. So please join me in giving a warm welcome to Mr. Justin Dyer. Hi, Justin.
Hi, Abhishek. Thanks for the
Hi.
introduction.
Thank you so much, Justin. Over to you.
Okay. So, hi, everybody. I'm super excited to be here today. I'm happy to see that many are interested in learning causal inference. So, what I prepared today is very brief introduction without going into a lot of theory. I just want to run some code, do some simulations, and show you some interesting things that might change how you think about your work in data science, specifically in building predictive models. And at the end, I would like to open up for a few questions. And also, I will be giving away a copy of my book. So I think the best part is at the end. So I invite you to stay with us for the full hour. And in the meantime, don't hesitate to ask questions or jump into the conversation if you want to add something. It will be my pleasure. And we can dedicate some extra time at the end to answer any additional questions that we haven't touched upon in the webinar. So just so you know, right, there's in Teams, you can use the chat. There's also the Q.
Yeah,
Yeah,
it's fine.
Okay. Yeah, it did it automatically, I think. Okay, so yeah, I was saying there's the chat and there's the Q&A section, and you can also raise your hand or react with the Microsoft Teams interface. So let me share my screen. I'll just need to set this up. Okay. So here's the outline for today. Does everybody see this clearly?
Okay. Yes.
Perfect. So we just did the opening. So the main portion will be the simulation. So we're going to discuss three concepts that we're going to learn through simulations. And at the end, we're going to discuss what this means for your work, and we're going to do the final wrap up, the giveaway, and the Q&A section. So before jumping into the code, I want you just to open with a little question. So let's look at the first table here, and we're asking the question, which model is better to predict Y? Okay, so the first table is just a preview of the data. Okay, so we have W, which seems to be binary. We have Z, which seems to be a numerical variable, and we have Y, which we're trying to predict. So one intuition we could have, or one idea we could try, is to fit simple linear regression model, which we will do together in a second. But assuming that we fit two candidate models, so one is the regression of Y on W, and the second one is the regression of Y on W plus Z. And the question we ask is, which one of these models is better? Now, you can look at the results for a few seconds. So the first result here is the coefficient for W. And here are the coefficients for Z. And we see that, well, here this is not applicable because Z was not a part of the model here. And finally, we have the R squared. So one thing you might have learned is that higher R squared is better. And of course, it is in a sense. Here we have an extremely high R squared. So this model fits very well. Okay. Now you might think, well, this is very high. It might be overfit, etc., etc. But if we just keep it to the R squared, we're going to maybe use this model as a better predictive model than the first one. Okay. We added extra information from Z, and we think that this improves the model. Okay. So let's keep that in mind, and we're going to see why this is wrong in the causal inference context. Okay, so this might be where the surprise happens. So I'm going to start the simulation. So we're going to do some coding together. So let me just adjust my screen share. Okay, now everybody sees on the left my code and on the right the notes.
Yes.
Okay, so
Yes.
perfect. So I'm using R for the code, but I did on purpose to choose very basic examples that could be done in any statistical software. It could be done in Python or anything else, because the important thing is more the ideas more than how we code it. I used R because I already made this example in R for my book, so it was easier to reuse, but it's very simple to do this in Python also. So what we're going to do, we're going to run different simulations to show how these different structures can lead to certain biases, even when our models have high goodness of fit. So here it will be R squared. So we're going to discuss the three structures we mentioned in the outline. So we're going to discuss a collider, a confounder, and a mediator. So the previous example we did was the example of what we call a collider. So we're just going to introduce a concept that is very important in causal inference that you might have heard about or you might not, but it's the idea of a directed acyclic graph. Okay, so this is a fundamental tool, and you might have heard also about structural causal models. Okay, so together, directed acyclic graphs and structural causal models serve as our assumptions, or our thoughts or our ideas about what are the cause and effect relationships between our variables. So this is a very simple example because there's only three variables, but it shows the fundamental ideas that you need to know if you want to use causal inference in your work. And by using these methods, we hopefully can obtain better idea of how our variables are related in our system that we're working on, for example, in a scientific context or in a business context. And it can help us to make better decisions to optimize certain outcomes, such as profit, for example. So recall that the example we introduced used three variables, right? We had W, Y, and Z. And the directed acyclic graph, so the DAG, is simply a representation of these three variables that we connect with arrows if we believe that there is a causal effect. So here, for example, knowledge of the system beforehand, before we get into the statistical modeling, or before we start running a machine learning algorithm, we could already have an idea, an intuition, thanks to subject matter experts or thanks to previous work that we do about how the variables are causally related. So we would, for example, in this case, say that W is a direct cause of variation in the Y, right? The outcome that we're trying to model, which we've called Y. But it is also a cause of the variable Z, and Y itself is a cause of the variable Z. And a variable that has this structure, that is receiving two arrows into it. So a variable like Z, which is the effect of both W and Y as causes. This is what we would call, in the causal inference literature, a collider. Okay. Now, there is some formal definitions that I discuss in my book, or other causal inference books will do this more formally. So I would invite you to go further if you need. But for the purposes of today, we will keep it simple. So what happens in this case? So let's start the simulation. So what we're going to do is that we're going to come here. We're going to simulate the data that respects the process described by this directed acyclic graph. Okay, so we're going to do this step by step. So we're going to start with 100 observations. Okay, so this is something that we could change if needed. And we're going to introduce a treatment effect that we're going to control, okay? And we're going to explain why the goal of causal inference is to estimate this value correctly, and what does this mean for practice. And this is the ground truth. This is what we're going to try to use as a measure of how good is our model. Okay, so rather than R squared, we're going to use the simulation to see, are we estimating this treatment effect correctly? If yes, what does this mean for our process, our decision making in the company? And then we're going to simulate all the other variables. So we're going to do the binary treatment. So this is simply saying to simulate 100 times a binary variable that is 0 or 1 with probability 1/2. So this could be seen as 100 coin flips. And this could be our treatment variable. Okay, so this is, for example, the customer was part of the ad campaign. Okay, so if they were a target, we say 1. If not, we say 0. Okay, so if they were exposed to the ad campaign, we consider them to have received a treatment. We put them in a treatment group. And if they were not exposed to the ad campaign, they will serve as control. Then we're going to simulate our outcome model. And we're going to put a little bit of noise just to make it a little bit more realistic. So what this means here, so we're going to simulate the outcome Y as a random normal variable 100 times, and it will be equal to have a mean equal to 2 plus a treatment effect if you are in the treatment group, and it will simply be 2 if you are in the control group, and we're going to give it a standard deviation of 3 plus a little bit of noise. Okay, so this mathematically, right, would be something like we assume that our outcome follows the model 2 plus 5 times the treatment plus noise or uncontrolled variation. So now we have simulated W, which is our treatment variable, Y, which is our outcome, and we will simulate the confounder, the collider. Plus noise. Okay. So, sorry, there's a little mistake here. So what we're doing here is we're saying that Z is equal to 20 times the treatment plus 20 times the outcome plus noise. Okay. So what happens here is that we're creating a model that respects the directed acyclic graph that we have on the picture, right? Because if we look at W, so W is just a treatment indicator. There's no cause of this variable, so we just simulate data. Whereas Y needs to be a function of W, right? Because W is causing change in Y. So we encode this by making Y a function of W. And likewise, Z is a function of both W and Y. So we're going to encode this by making Z a function of W and Y. So here I chose simple linear functions, and we're going to fit linear models because the important thing here is less about the statistical ideas of finding a good model fit for the shape of the relationship, right? We could do nonlinear models, or we could do trees, right? We can use a whole bunch of models to do this, but to keep it simple, let's keep the most basic, just linear models, and we're still going to run into some of these important ideas that could affect your work. So now let's put all this in a data frame, just so it's easier to control. And now let's start fitting models. So if we just want to understand the effect of Y on W, we could just, wait, sorry, I'm going to do it like this. We could just fit a model of Y on W. Using the data, and we could ask for the summary of this model. Maybe just the coefficients will be sufficient. Okay, so this would be the output. So this is what we would call the unadjusted model, right? So simply modeling Y as a function of W. Or we could also adjust for Z, or add, or we could say also, or adding Z as a predictor. Maybe let's take the full summary. It will be better. Okay, so we have our two models. So this is the first model. We see that the multiple R squared and the adjusted R squared are about 32%. And if we look at the second model, the R square is almost 100%. Okay. Now, if we're interested in knowing how the treatment, or how, in this case, it would be the ad campaign, for example, impacted the outcome Y, it can be sales, it can be conversions, click-through rate, etc. Well, we're going to study the coefficients, and we see that here the coefficient, which we know that the true value is 5 because we put it in the simulation. Here we have a value pretty close to 5. There is some noise, so it's not a perfect estimate. But here, the estimate of W, the coefficient is negative, which is completely off the mark because we know that the real effect is 5 in the positive direction. But the model fit is better. Okay, so what's happening is that when you do statistics, you are doing a correlational analysis, right? So a linear regression or any machine learning technique for the matter will be simply capturing associations, right? Or correlations in the data. So the model can't really make the difference between, is it Y that is causing variation in Z, or is it Z that is causing the variation in Y? So Z is helping the model predict better, right? It's improving the fit almost to 100% perfect fit, simply because there is a strong correlation between Y and Z, which is to be expected because Z is caused by Y. But this correlation is not causal. So the price to pay for exploiting this correlation is that we are distorting the effect of W on Y, which is the true effect that we're interested in estimating in causal inference. Now, why are we more interested in this in causal inference, right? In understanding a parameter estimate like the parameter of W? Well, it's simply because W is the treatment variable, so it has a special status. If we want to understand how the ad campaign influences Y, we want to understand what is the coefficient of the W variable. So when I change W, how does Y change? Now, here, -1 is completely off the mark, but here we are closer. So this would mean that in putting a user in the ad campaign is actually increasing the outcome Y, for example, the sales or the click-through rate, by about 5, whereas this model is saying that it is decreasing by about 1. And these lead to completely different decisions, right? If we estimate a pretty strong positive relationship, then we might want to put more people in the campaign, put more budget in the campaign or something. But if we find a negative relationship, we might hold back on the campaign, we might stop it, etc. But because we simulated the data ourselves, we know that this is misleading and this is the truth, or at least closer to the truth, right? Because we created a simulation where the treatment effect is 5. Okay. Now, if you study causal inference literature, they will explain that in a model like this with a collider, you should not put the collider in the model, okay? Because this will create a bias for the causal estimate of the effect of the campaign on the outcome, okay? Another example of this is if you do a clinical trial or you do a scientific experiment where you measure people over time. If people drop out, so if you do an A/B test where you measure people over time and they drop out, which is a little bit less common, or at least doesn't happen in the same way that it would happen in a medical trial, in which I work a lot. If you only study those that remained in the trial, you could potentially be causing a sort of bias like this, even if you're not explicitly putting a new variable in the model, but simply by only looking at people that completed, right, the trial, you could be introducing a bias like this, which is very hard to know in the data because there's just people that are not in the data because they didn't complete or they exited the experiment. So keep in mind that this is very problematic and it requires a lot of thinking about these causal structures to understand, am I estimating the right thing? So let's move on to the next structure. So these are what we call confounders. So we still have the same kind of setup where, whoops. Second, here we go. We still have the same kind of setup where W is a cause of Y, and we want to estimate that effect, right? So W is again going to be our treatment. But here we have two extra variables, Z1 and Z2. And notice that the structure is different. Now this time, Z1 is a cause of W and Y, and Z2 also a cause of W and Y. Whereas previously, we had Z was caused by W and caused by Y. Okay, so notice that difference. And let's see how this impacts the simulation. So we're going to do something extremely similar again, just because we don't need to make this complicated to see what's going to happen. So we're going to do pretty much the same thing. We're just going to take 100 and we're going to put a treatment effect of 5 just to keep it similar. Now we're going to simulate two confounders that are going to be just a normal random variable plus noise. And the noise is, again, just to make it a little bit more realistic. And we're going to simulate exactly the same variable for Z2. Okay, so these two have the same distribution and they're independent from one another, right? They don't have an impact on one another, so they're simulated independently. And now we have to follow the structure of the diagram. So Z1 is causing W and Z2 is causing W. So W should be a function of Z1 and Z2. Now, how to make this a binary variable? So what the trick is that we're going to simulate a random binomial, but the probability will be using the logistic function for the quantile. And like such. So we're going to use a random binomial, which is going to give, it's going to be like a coin flip. But, so we're going, sorry, I'm going to start that over. So the random binomial is going to be simulated 100 times for one variable. So it's going to be 100 coin flips. But the particularity here is that each coin flip will have a probability of being heads that depends on the confounders. Okay, so if we put people in the treatment group based on other variables, this will affect their probability, and we're incorporating this in the simulation like this. Okay. Finally, we need to simulate y. So y here has 3 arrows, so it's going to be a function of w, of z1 and z2. So to do this, we're going to simulate a normal variable. And the mean, again, will be the treatment effect times w plus 20z1 plus 10z2 with a standard deviation of 3. And we're going to add, again, the same noise just to make it more realistic, to just add noise everywhere to create more variability as we would have in real life. So here, again, if we had an equation, it would simply be that y is 2 plus 5 times the treatment indicator plus 20 times Z1 plus 10 times Z2 plus noise. Okay. So this is the true model. And this time we're going to run 3 linear models to compare them. So we're going to start with simply, so let's create the data before. Just to simplify. So this one, simply a model of y on w. Okay, so if we just look at how the regression of y on w describes the data, then we're going to look at what happens if we add one confounder. Okay, so if we just add one extra variable, we expect the R squared to increase, right? Because we're adding predictors. And for the causal structure, we're going to look how this impacts the estimate of W, the treatment effect through the coefficient. Now, since Z2 is basically simulated from the same distribution as Z1, we're not going to look at it separately, but we're going to look at what happens if we put both in the model. And sorry, we're going to put both in the model. And this is going to tell us what happens to the causal estimate when we control for Z1 and Z2. Okay. So this should be plenty. Let's run this. Let's just make sure that everything looks okay. So this is our first model. So the R squared is hovering around 50%. And the estimate for the treatment effect here, right, the coefficient for W is 53. Okay. So we know that the true effect is 5. Okay, so this is strongly overestimating the effect. For the second model, okay, so as expected, the R square increases. So we see that it's close to 90%. And the treatment effect is closer to 5, but it's still far, right? We have a 24 plus, and the standard error is smaller than 3. So the estimate of 5 is way out of the confidence interval. So this shows, because we know the truth in this example, that we are severely biased for the effect of W on Y. And the final model, which we could call maybe the full model here. Okay, so of course it has super high R squared, right? Because basically we know that this is the true model for Y in the data we simulated. But look at how the treatment effect is also much closer to 5. So basically, by adding Z1 and Z2, we were able to eliminate some of the causal bias and get a clear estimate for the causal effect of the treatment on Y. Okay. So this is what we typically call confounding. And if, again, I explained this in my book, you can find this in a lot of other books or blogs or online resources. This structure, when you have a variable like this, that is a cause of the treatment and a cause of the outcome, we call this a confounder. And the theory of causal inference tells us that this model should be adjusted for. This variable should be adjusted for in the model. And so should Z2. Okay, so if you know the causal structure, here you adjust for Z, but here you don't. Okay, but if you don't know the causal structure, they both give you extremely high R squared, right? So in this case, the R squared is leading you correctly, right? Because the true model is the one that we adjusted. But if you're in this context, the R square is misleading you, okay? And this can be true of any other goodness of fit, okay? To reiterate, the problem with goodness of fit for causal inference is that goodness of fit is purely correlational. It's purely associational. It's trying to sorry, I was distracted. So if we just follow the goodness of fit, the goodness of fit again is exploiting any correlation it can find. So here it's exploiting the correlation to better predict Y, to have a better fit at the expense of biasing the treatment effect, which is what we're trying to estimate correctly. So any statistical method does not know what was the diagram used, right? What is the true diagram? This is knowledge that we bring to the table. And obviously, there are many ways to extract this knowledge, but we need to have it in order to do causal inference. Okay, so before I jump to the final example, I will just address a few questions in the confounder DAG. If we don't have the arrow between W and Y, does it continue to be a collider? Okay, so Marcio, so let me just clear this up. So if there was no arrow, if there's no arrow here, okay, then the treatment effect would be 0. And adding Z to the model would create a bias. So this could, for example, bias by saying, oh, there seems to be a treatment effect while the true effect is 0. So yes, even if there's no arrow here, there is still a bias. And in this DAG, what would happen is that if there is no arrow here, so if the true treatment effect is 0, what would happen is that Z1 and Z2 would be creating a spurious correlation, right? Would be creating a bias that could mislead us to thinking there is a causal effect. But if this is the true data generating process and there is no arrow here, so the treatment effect is 0, then a model of Y with W, Z1, and Z2 should be able to recover the fact that the treatment effect estimate should be 0. Okay, so you still need to do the right model to be able to see the 0 treatment effect. Okay, so I hope that clears it up. Okay, and finally, the final example. This one is the trickiest. It's a mediator. So here we have a variable m, which is which we will call a mediator. So w has an effect on m. M has an effect on y, and w has an effect on y. Now, let's simulate this quickly. So it's going to be, again, very similar to what we did. So I will go pretty quickly. Oops. So again, W here will just be 100 coin flips. Y will just be exactly how we had done it in the first example. So just an outcome model plus noise. And let's do M. So M is going to be just a random normal variable as a function of the treatment plus noise. So let me just make sure that everything works here. Yeah, so this is our system. So again, W, just 100 coin flips. M is a random normal variable that will have mean 2 if the person is treated, and have mean 0 if it's not in the treatment. And Y will be a function of W and, sorry, forgot this, and M. Okay, so again here, Y is just a function of W and M plus some noise. So we will put this in a data frame just to simplify again the coding. And we will again fit 3 models. So we're going to do just the basic model without M. We're going to do the model with M. And this time, to change things a little bit, we're also going to do the model of M as a function of W. Okay, so we're going to use this to explain a few concepts. So following the DAG, we have y as a function of w and m. We have y just as a function of w, which we expect could be problematic. And we're going to model m as a function of w, just to show something here. So I have a question. Okay, we're going to do the question in a moment. Did I make a coding mistake? Yeah, treatment effect. So we simulate this. This is the first result. We see that R squared is around 50, and the treatment effect estimate is close to 11 when we expect it to be around 5. If we look at the second model, this time this is the correct model because y is indeed a function of w and m. So the model where we put y as a function of w and m is the correct model. The R square is 80, which is higher because we added a variable, but this time this variable was okay to add it, right? We get a treatment effect estimate of 5 as expected. And in the final model, we get an effect of W on M, right? W on M of around 2. And this is what we had put in the simulation, right? The coefficient of W on M was around 2. But also more interestingly is that if we multiply this times this, okay? Wait, no, sorry. This coefficient, so when we do W on M, if we multiply this coefficient by this coefficient, we would get what we call the indirect effect. Okay, so this is a little bit more complicated when we have mediators, but W has an indirect effect through the mediator, and W has a direct effect on Y. Okay? So this adds another layer, right? Are we interested in the total effect, the effect of when we consider M or not? Or are we interested in only the direct effect? Do we want to break down the effects in direct and indirect effect, etc.? This depends on the use case. So for example, if the treatment is a weight loss program, or I mean an exercise program, and we want to know, does this improve a patient's blood pressure, for example? We could assume that simply exercising improves your heart function, so that can improve your blood pressure. But we could also say, like, for example, that the treatment program improves your weight, so you lose weight, and weight reduction helps your heart perform better, so your blood pressure improves. Okay, and we can study a whole bunch of pathways for how exercise improves your your heart function and your blood pressure, etc. And this would require an appropriate DAG with all the variables, and we could try to estimate all the effects if we had sufficient data. So that ends the simulation. So what do we do about this? So the variables, so let's give these final tips before wrapping up. Okay, so what should you do about it? Okay, so I want you to start thinking about if the model you're making is to try to estimate the effect of some decision or of some variable on another, you should be thinking causally. And when you do that, the variables you include become assumptions. Okay, they're not simply there to help improve prediction accuracy, to help improve model fit. They have a purpose in the causal system. And there are many other structures. Okay, so we saw confounders, colliders, and mediators. And this was just the surface. There's the whole other set of structures, chains, forks, M-bias, etc., that I discuss more in detail in my book. But there's also other great resources so you can start learning how these structures appear and how they will potentially mislead you or bias the estimates when you're doing causal inference. Okay, so we can open up to questions. So we have 10-ish minutes for the questions. In the meantime, I want to explain how I'll be doing the giveaway from my book. So if you're interested in receiving a copy of my book, sorry, I'm just going to stop sharing. So while you put down your questions, so I will choose randomly someone that's interested. So if you could put in the chat those that if you're interested in receiving a copy of the book, so that I can put you in the giveaway. And for the others, I just want to show you. So the book. Wait, sorry, this is the wrong screen. Okay, so this is the web version. So you would have access to the web version if I draw your name, and there's a PDF version. So this is, for example, the chapter where I explain everything about the directed acyclic graphs. So as you can see, there's a lot of theory around this, and at the end, each chapter, there's always a case study. So here, what we did today is part of the case study of chapter 3, where we explain these different kind of DAGs and biases, and I do some simulations, and you have access to all the code similarly to what we did today. But you'll see there's a lot more material because we only had 1 hour today. And for the others, this is my page, and you can get the introduction for free. It's about 50 pages or maybe a bit less for those that want to read that. So you can just download it for free. It will be my pleasure. So now let's jump to the questions. So I will add the link for those that are interested in getting the first chapter free. And now we can use the last moments for the questions. Okay, so let me just scroll all the way back up. Nice to meet you, GetNet. Thanks for sharing your LinkedIn. Could we get the document? Yeah, so we're gonna share what we can after, including the recording. Okay, so first question from Reshmi: which causal discovery algorithm takes care of confounder, GS or other? Could you elaborate your question? I'm not sure exactly what you mean. Do we need mandatory domain knowledge before forming the causal structure? I mean, if you don't know, you could try different diagrams and see how they impact your causal estimates, in the sense that if I change the diagram, does it change what the causal inference theory tells me to put in the model? If so, then you're in a bit of a bind because you don't have the proper domain knowledge. And this is very common in practice, where you're not sure about how to draw the diagram. So you could either make hypotheses or assumptions about this, or you can try to collect more data, perform experiments to try to help you understand the causal structure better. But yes, you need to assume a causal structure for these methods to work. So whether this is plausible, whether this is rigorous and reliable or not, really depends on the case-by-case basis. Okay, so wow, a lot of people interested in the book. That makes me happy. So I'm all gonna put you in the draw. How can we identify or select mediator variables? So this is a question from Dinesh. Is using correlation or covariance sufficient? No, so this is exactly the problem, is that the causal structure is sort of a level above the correlation or the covariance structure. So two variables could be correlated very strongly without being a cause of one another. So that's why you need a priori knowledge. You need to build the diagram based on your best knowledge of the situation before looking at any correlations. Kandasamy, thank you for the nice comment. Gabriela, in a medical context, how does causal inference play a role relate to prediction models for personalized medicine? Should we first estimate the causal effect to then include it in the prediction model? Yeah, I mean, if we don't know that a treatment causes a benefit, what's the worth in personalizing it, right? So, yes, we have to estimate the causal effect. I think the promise of personalized medicine is more in trying to use personal information to have a more individualized effect estimate to help guide personalized decisions, but it's still causal in nature. Nikolai, what are the main caveats when using meteor analysis when running multi-level regression models? Just mediation analysis is difficult. You need a lot of data. And if your statistical model is hierarchical or multi-level and you're adding a lot of estimation of covariance structures and complications, the more you do this, the less you have degrees of freedom. So when you're going to start to try and estimate direct effect, indirect effects, etc., you're going to have less and less precision as you complicate your statistical model. So that would be a caveat. Sid, from a regulatory perspective, what evidence or documentation do you think is most persuasive when presenting a causal inference-based RW to agencies? This is a really big topic. I would say that the best is to be transparent and open the discussion with the regulators early, because we don't have all the apparatus of a randomized trial. It's much more reliant on trust and transparency. Nilton, when parameterizing M, why have you included twice the number 1? Shouldn't 1 be 0 to be the control? That's a good question. Yeah, I don't understand what you mean by twice the number 1. Sorry. Okay, so I think that goes around the questions. Oh, there's some in the Q&A. Does the mediation imply an interaction between W and M? Not necessarily. It depends on the nature of M. For unmeasured confounders, e-values, are they sufficient? I mean, they're a step in the right direction. I think sensitivity analysis of confounders goes above just giving e-values, because e-values only give you how much you need to eliminate the effect completely, which might not always be interesting. So be careful with that. Shishir, do we need DAG causal inference for every model to get correct prediction model? No, right? The goal, if you're not trying to understand the cause and effect, or you're not trying to understand how a decision or an intervention or a modification of something is going to impact another variable, that's fine, right? Like many prediction models don't really care about causality and could be super important. Like, for example, I don't know, like Uber sends me a push notification predicting that I might use the service if they do. Yeah, maybe it would be better if it was causal, but it doesn't mean that it cannot increase revenue even if it's not causal. Yushu, we can only determine by domain knowledge. Yeah, there's no statistical way to test this. Okay, so I think that goes over the questions. The second R noise is a random noise. Oh, okay. Yeah, I mean, I think it's fine to just add random noise. You can stay after if you want to discuss it a little bit more. Okay, so we could end there since we're a little bit over the hour. So thank you everybody for the questions, and feel free to connect with me on LinkedIn. I can send you my profile, and if you have other questions, you can just send them on LinkedIn. I'll try my best to answer them. For those that are that expressed interest, so I will be giving away a copy of the book. I'll try to do this today, and maybe we can get in touch with you as soon as possible.
Yeah, Justin, just give me a minute.
Yeah.
Yeah.
Okay, thank you, everybody.
A big thank you to Justin. A big thank you to everyone who joined us today. So there's a wrap-up post which has been inserted into the chat box. You can keep the conversation going with the people who has joined us. And it was a wonderful session. I also got to learn a lot of things in the terms in the world of causal inference using data and R programming. So thank you, everyone. Please get yourself engaged using the wrap-up post. Get acquainted with all the people who were a part of this active session. Thank you, Justin. Thank you once again.
Thank you.
Thank you. Bye-bye. Take care.